Hello everyone, this is the second lecture of week 15 of the final week, and on this lecture we will look at the matrix exponential function, or shortly speaking the matrix exponent. So we have developed various ways to extend techniques for scalar differential equation to systems, and in this lecture we'll introduce the right notation which makes the formula for systems and for differential equations identical. So for example, for differential equations, let's say when we solve simple equation like y prime of t is a y of t, we know that solution is y of t is some constant times e to the power at. And for systems, now x is a vector and a is a matrix. We want the solution be e to the at, the matrix, and some constant vector c. So what is this thing here? And this is the matrix exponent. Let me give you the definition of this matrix exponent based on the definition of just simple exponent. Recall that from calculus, the function has the following expansion. So this is 1 plus at plus a squared t squared over 2 factorial plus so on. So this is infinite series and it converges for any t. This is proved in calculus. And now we define the matrix exponent similar way. So e to at, this should be 1, and 1 in matrix is just identity matrix, right? And instead of a here we write the matrix A, and instead of a square we write just a square, and so on. And here we have series of matrices. And using matrix calculus, one can prove also that this series converges for any value of t. So this is definition of matrix exponent. Okay, next question. How we can find this matrix exponent, and is it indeed satisfy that this is this matrix in the solution x of t of this homogeneous system? So the first thing, the simplest case when we can find the matrix exponent is for diagonal matrix. For example, let's consider matrix A to be -1, 0, 0, 2, and let's find E of at. Let me write it as series, and from 0 to infinity, a to the power n, t to the n over n factorial. And we know that, for example, the square of the diagonal matrix is just the square of the entries on the main diagonal, and so on. An is, sorry, it should be square here. And the nth power is obtained by taking n power of the entries on the main diagonal. So in fact, this series here is nothing as the matrix, where the first one here is the series -1 to the power n, t to the n, n factorial. And on this place the series 2 to the n, t n, n factorial, and zeros here. So this is in fact the matrix. This one is minus t, e to the minus t, by definition of exponent, is 0, 0, and e to the 2t. And in fact, it can be proved that if we have diagonal matrix, let's say n times n matrix with a1 and so on an on the main diagonal, then the exponent of this matrix is just taking exponent of the main diagonal and so on e to the an t and zeros elsewhere. So for diagonal matrix we can easily find the exponent. Let's now look at some properties that also can be proved using a matrix calculus. And the properties of matrix exponent are very similar to the properties of usual exponent, but with just some differences. So assume that let A and B be some n times n matrices, and let's say T and S are numbers. So the first property that we can get, a simple property, if we take e to the a times 0, we just get e to the 0. If we look at the definition of exponent, you will see that this is indeed just I, because all other terms contain t, which is 0 now. So this is identity matrix. So this is similar to e to the a times 0 is just 1 in numbers. Okay, for part B, e to the a, let's say we have here sum of numbers. This is the same as e to the at times e to the as. So this is similar to e to the, let's say, a plus b is e to the a times e to the b. Sorry, e, not a here. And in C, let's say what else we may have. If we take e to the at, and if we want to find the inverse matrix for this, this is nothing but e to the minus at. And if we take, let's say, sum of two matrices here, then this is equal to e to the at, e to the bt, but only in the case if a and b commute. And e, the property e is if we have, let's say, e to the, let's say, R identity matrix and t, then this is the same as e to the RT. R and t just numbers. Okay, let me use here, let's say S. We're taking S to be numbers. And times identity matrix. Okay, so these properties are quite important for exponential matrix. And the next property, which is also important, let's find derivative of e to the at. So what we do, we just use the definition. So this is a series I plus at plus a square t square over 2 factorial plus, let's write also, t cubed over 3 factorial plus so on. Somewhere here we have a n, t to the n over n factorial and so on. So we have to differentiate the series. And of course, when we differentiate this I, we get 0 matrix. When we differentiate this at, so since this is linear, we get just a. And when we differentiate this, we get a square times 2t, derivative of t squared is 2t over 2 factorial, plus a cubed 3t squared over 3 factorial, plus so on, plus an n times t to the n minus 1 over n factorial, and so on. So what can we do here? First of all, we can cancel in each term, we can cancel this coefficient and the 1 factorial here. So here we have 2 factorial, here we have just 1, and here we have n minus 1 factorial left. So what do we have here? A plus a square times t over just 1, right? So just nothing. So just times t plus a cubed t squared over 2 factorial plus so on, plus a to the n t n minus 1 over n minus 1 factorial plus so on. And what can we do now? We can take out this a, what we left inside the brackets. Here we have identity matrix. Here we have just one a left. Here we have a square plus so on plus a, and here we have n minus 1 power left. So in fact here what you can say that this is exactly the same at what we started with, right? The same series. So this is at. So therefore the derivative of this is a times e to the at. So therefore this thing e to the at satisfies the system x prime of t is a x of t. So indeed x prime of t is a times x of t, right? So indeed it satisfies the system, and of course if we multiply by any constant vector this thing, it will also satisfy the system.